So hi everyone, my name is Urvin and I'm making this video to demonstrate my project page of task 6.1p. So let's move on to the project idea which I want to discuss is the Termiflow. It's a smart fertigation system which will allow us to monitor and have a precise control over the crop production. So first of all, okay, so let's first of all talk about the problem domain and the current practices. The problem domain basically involves mainly highlights the 2 points, which are the precision, quality, and cost, and the production as well. And so, talking about the current practices, currently there is manual control over the cultivation, like farmers use drip irrigation method and manually supply the nutrients, components, and water as well, which lacks the precision, which lacks the quality, and it's not consistent everywhere where we are growing the turmeric. But because every farmer has different checks and considerations as well, but this but why we are talking about these problem domain? Because growing turmeric requires precision, and through precision irrigation, turmeric growers can protect the crops from a variety of disease, improve the quality of the turmeric, and even provide the real-time checks on that production through every single moment, and this enhances the overall quality of the turmeric and even the nutrients, because turmeric is a really helpful product that is being used worldwide and in many parts. And so this was the all. And the one last point was that the water deliveration or any component that is required for production is not delivered to the crop root zone of the turmeric, which is really a necessary part for the quality. But through these current practices, these methods are really lacking on such points, and these are some gap opportunities which we are introducing to eliminate those current practices and enhancing our production by using this type of embedded system. These are some points which are no real time, and there is no decision making, efficient, precise decision making, and we are reducing the cost as well. And this embedded system provides us with the automation as well. So let's talk about the proposed solution. Here, so here I'm using the Raspberry Pi 4, which is the main decision maker, and the Arduino Nano 33 works on the decisions of the Raspberry Pi. And Raspberry Pi is, suppose there's a field in which on the one side there is a small office, and around that is the yield, is the field where we will be cultivating our crop, and this embedded system is designed accordingly to this structure. And these are some of the components that we are using the pumps, we are using the real-time communication, and even the fault tolerance that I would like to mention. So these are main components, and the communication protocols that I have been using is the low range to connect the Raspberry Pi and the Arduino Nano 33 IoT. And beside that, we can even use the MQTT as well. And some of the other communication protocols are the I2C, SPI, and UART. UART basically if is for the low range because it involves the TX and RX communication, and I2C is for some for the other components that we are using in another sensors. And for some open weather application, we will be using the HTTP protocols to fetch the API, and we will be using webhook URLs to get the data and to get the decision done by the Raspberry Pi as well. Along with that, we have some sort of alerts that will be sent through to the mobile phones or any other device by using the protocols, either IFTT or by using, or we can use Node-RED as well. I'm currently deciding to use the Node-RED because it is more efficient. We can even customize that. It's an open source. We have also discussed about it in our previous task as well. So So let's talk about the interface that will be provided by the Raspberry Pi, because the Raspberry Pi will be kept in the office, and and it will be connected with the monitor, keyboard or mouse, because we want an interactive user interface which will provide us lot of components like the real-time dashboard, even the even some radio buttons as well, and we'll get all the messages, and we have some interactive, because we want to customize our interface or even providing any command to get the manual control over the whole system. We can use that interface to turn on the system by just turning on the pumps, controlling it manually, delivering the fertilizers manually. We just need to hit one button on the interface. We don't have to go on the field and just to split the fertilizers and the buy manually. That's not the case. We want whole automation and even some manual control with very less efforts, saving the cost, saving the production, improving the quality, and improving the precision as well. So this is my whole pre-system diagram that I have imagined that it would look like this. This is a Raspberry Pi. This is the connection between the Arduino, and this is how the data will be sent and the data will be received. This is a two-way communication, which is the full duplex communication, and we are generally focusing on the full duplex communication, and the right protocols to use for that are the MQTT or either low range. And this one is the interface, sorry, this one is the interface, and these are some components that are being connected via Arduino, because it will be kept outside of the office in the field, and it will work according to the decisions of the Raspberry Pi, and it will send confirmations. But the point that I have been missing was the fault tolerance that I want to discuss. It offers 2 to 3 points of the fault tolerance, like if suppose there that the Raspberry Pi and the Arduino have been disconnected, then how will the system will work? How the Arduino will be able to make the decisions, and how the Raspberry Pi will be able to provide the interface in the office. So in case if the connection between the Raspberry Pi and the Arduino is not there, then we'll get the suitable messages in the interface, and the other messages that are being displayed, uh, and other messages are also being displayed for other errors as well. But meanwhile, we want that our crops are being real timely monitored. Even if we have this fault, then we will just get the Arduino on the basic logics, like comparing the soil moisture and even other components nutrients by some certain thresholds, and getting all of the control on the Arduino itself. But here we will not get the real-time data being transferred to the interface, because we aren't having any connection. But still, we want our crops to at least get the real-time monitoring and caring. So the whole tasks will be sent will be taken through the Arduino, which will be very basic, but still it would save a lot of quality and a lot of precision on the growth of the turmeric. And the other fault tolerance that I would like to talk about is the confirmation of pump fault detection. If there is any fault observed in delivering the components, like Raspberry Pi has given the decision to get the pump and get those nutrients to the field, but still, if there is some fault that our pump is not behaving properly, the nutrients are being not sent properly, then Arduino verifies the operation by checking the current flow sensor or the relay feedback, and will give the message to the Raspberry Pi, and it will show the error in the interface if there is any error observed in delivering nutrients. And hence this is also the another point for the fault tolerance. So here's my architecture for the system. We will be using open weather API. We'll be using the interactive GUI, which will be displayed on the monitor, because we want the interface to be most easy for the use for any farmer and more interactive, that the system can be controlled with very less efforts, and we don't have to move to the field to for the growth purposes. And this is how the communication is being done, and this is a really having potential for growth of turmeric, because this project is basically designed and all the precisions are being perfect will be perfectly designed for the growth of turmeric, like the how much frequency the nutrients have to be delivered, how much frequency if we want that we want the water to be delivered, and all this with along with that we will be using decision logic with the Raspberry Pi. Like if there is an expected rain or any sort of event, if that doesn't require any component, like there is rain in 1 hour, then the open weather API will fetch that information. The Raspberry Pi will take the decision that we don't need to provide the water because we are expecting a rain, and if that rain is expected, then we'll get a message in the interface, and then we don't have any need to deliver the water because it will save a lot of amount. And if we think that after sometimes it is given that after 1 hour we don't experience any rain, then the Raspberry Pi will immediately tell the Arduino, and the respective components will be delivered, and along with that a real-time check will be displayed with many graphs and many radio buttons, customization and everything. This is the whole project in short. Thank you for watching.